Okay, so just state that right now all the circuits will be chosen to give systems of linear equations. And this basically means that you're not going to have to use a loop that has a capacitor and an inductor in the same, in the same loop. So I'll say by avoiding the necessity to use a loop, with both a capacitor and inductor. And the reason for that is pretty simple. The capacitor is controlled by the charge. The inductor responds to the rate of change of the current, or the derivative of the current. Now, the current is a derivative of the charge. So the inductor responding to the rate of change of the current is going to respond to the second derivative of the charge, and that would give you a second order equation. Okay, so the capacitor is a voltage drop. I'll just say delta V for voltage drop. Is the charge Q over C. The inductor is L di dt. So if we try to use this and this in the same loop, we're messed up. Okay, now as an example of how we deal with the capacitor, instead of talking about the charge here, let's just do an example where we have a capacitance C and a resistance. Well, for a resistor, I didn't write it down, but we assume we know this, that, well, let's just write it down over here just for reference. Resistor, the voltage drop equals R times I. Doing too much linear algebra. Okay, R times I. So we move around this loop, and let's just say that this loop is part of a larger circuit. So we have a current I1 going through the resistor, and a current I2 through the capacitor. Okay, well, one way to write this out is that then the voltage drop say the loop equation, this circuit, if we're going around counterclockwise, is I1R minus Q over C equals 0. If we take the derivative of this equation, I'm just going to write it out. Derivative is R di1 dt, obviously, minus the derivative of Q being the charge on the capacitor, is going to be I2. Because, of course, the current through the capacitor is the rate at which the charge on the capacitor is changing. I'm going to write Q prime. Okay, so now we can write this loop equation in terms of I1 and I2. Okay, now that's not the way we did it in physics because we just dealt with the second order equations. And we were confining ourselves pretty much to just an RLC circuit in that course, and we could handle it that way. Within a loop, you either want to do it this way, when you have a bigger network of resistors, capacitors, and inductors, do it this way and get systems of first order equations with just first derivatives, as long as you don't have a resistor and an inductor and a capacitor in that loop. Okay. If you have a resistor, inductor, and a capacitor, you can't get away from having to do second derivatives of charge here and first derivatives of charge here. Okay. So the book is actually simplifying things a little bit by giving you circuits where it's always possible to do this. Now, in that case, let's just try to write out a circuit or sketch a circuit where that's feasible strategy. Okay, so let's just have a circuit that looks like this. Now we can have inductors, and we can have resistors. So there's a loop that just has an inductor and a resistor. And here's another loop. It's going to have a resistor and a capacitor. As long as we don't have an inductor here, we're okay, because we've got a loop here that has an inductor and a resistor, so that the voltage drop here is going to be proportional to the rate of change of this current. And here, the voltage drop across resistors is just going to be a multiple of the current. So we can set up this loop in terms of di dt and this one in terms of just plain old I. Over here, we got another current. And now we can do what I just did over here. We have a capacitor and a resistor in series, and we're going to be okay. We'd even put another resistor in here. As long as we don't put a capacitor or an inductor here, we're okay. If we put a capacitor and an inductor here, then there are only three loops that we can consider. We have this loop, or this loop, or this loop all around here. We can't use this loop because we have an inductor and a capacitor, but we can use each of the two smaller loops. So if we have an inductor here, we're going to get a situation where we have to use second order equations. We're going to get a system of second order equations, and we can't deal with that. So if we label these points A, B, C, D, E, F, question is, can we avoid loops with L and C? We can't use loop A, B, D, E, since we have an inductor and a capacitor. Let's go ahead and give this L here, call this R1, R2, and C. Fairly simple circle. Okay. So we can't use loop ABD and ABDE as an inductor and a capacitor. I'll use L. L doesn't stand for inductor, it's an inductance. So we have an inductance and a capacitance in that loop. We can use ABCF, which has inductance and resistance. And we can use CDEF. It has a resistance and a capacitance. We can't avoid L and C if we insert L, an inductor, in CF. So we put an inductor in here, then we have an L and a C in this loop. We have an L and a C in this loop. And to get the equations, we're going to need at least two loops. We could, and we can't put a capacitor. If we put an inductor or a capacitor in here, we're out of luck. Now we're not out of luck because we can set up a second order system. But right now we want to set up a first order system. Easier to handle. And I'm assuming the book doesn't deal with second order systems. I haven't look that far in the book because we're not going to get that far into systems. So if we put an inductor here, the loopy looking thing, put an inductor here, and then we have inductor and capacitor, and this loop can't handle it. If we put a capacitor in here, we've got an inductor and a capacitor in this loop, leaving us only, well, no loops that we can handle with first order equations. Okay, well, again, I went on with that just a little bit too long maybe, but it differs in this case from what you saw in physics to the extent that you haven't repressed that by now. Okay, so let's just look at the equation. So I haven't left myself an abundance of room here. But let's just do at least one loop. Okay, what about loop ABCF? Well, we need some currents. Okay, so we're going to have a current I1 through both this inductor and this resistor. And let me go ahead and put, the only thing we can put in here now is a bad looking resistor. Okay, so we're going to call this R3. Okay, so in this loop, we have a current I1 passes through L, the inductor and the first resistor. And then we're going to have the current I2 that comes down here, joins with that, whatever current is coming through here to form I1. And then we're going to have an I3 here. So now we've got three currents. And we see what each current does, the voltage drop around its loop. I'm going to make the convention without writing it that we're moving counterclockwise around each loop. So I'll just write counterclockwise loop A, B, C, D, F. If we go around counterclockwise, then we have current I1 through the inductor. And that means that L the I1 dt is voltage drop through the inductor. Plus R1 I1 plus R3 I2 is equal to 0. Can we still see all that? Yeah. Okay. Loop. Counterclockwise here, counterclockwise here, even though that arrow is clockwise. No, I said counterclockwise. Okay. Doing these loops clockwise. This is the way clocks go. Okay. And this is the way clocks go. So I'm glad I observed that. Otherwise, it would have been more confusing than it already is. Okay. Now, we have I3 that has to go from here all the way through here because there's no place for it to branch between here and here. So we have and now I've got to go to this convention here. Okay, I can write it in terms of Q, but if we remember this relationship, we can say that R2 times the I3 dt plus C times I3 It gives us something like voltage drops here. And of course, we're going to have to, that's too much to think about. Okay, I'm going to write it out in terms of Q, and then we'll take the derivative and get this equation. Okay. So I want to say that R2 I3 plus Q over C minus R3 I2 equals 0. So that I got this lip on the board and I just can't write a di3 dt, so I'm going to use the prime here and then we'll write it all out. So my I3 is a di3 dt, which I think you understand, plus Q over C, but dQ dt is the current through the capacitor, which is I3. And right there's our system. I'm wishing I had one of these other boards flushed, but I don't. So now I'm going to write out the system as it is. So there's another thing, and that is that I can express any one of these currents as a sum of multiples of the other two, actually as a sum or difference of the other two. I3 plus I2 equals I1, because I3 and I2 come in here and I1 goes out. And we'd write that, of course, I2 plus I3 minus I1. Sum of the currents into the node here is 0. This means, of course, again, I could say just that I1 equals I2 plus I3. So we could write it that way. We'd have a I1, we replace that with an I2 plus I3 here and here. And that might be the most efficient way to do it. If we don't like doing derivatives with an I2 plus I3, of course, it's no problem to do that. But if our taste leads us elsewhere, we could say then, for example, that I3 equals I1 minus I2. Okay, we can make our choice how we handle this node. So I'm going to make a note up here since I don't have room down here, and then I'll come over here. So it's usually safest to just use signs, use positive signs for anything comes into the node and negative signs for anything comes out of the node. Current can't accumulate at a node. Just go to Coulomb's law and see what happens if you accumulate current at an unprotected node as something besides a capacitor or the equivalent. Don't want to be within miles of it, even if you run a simple little 1 amp current for 1 second. If you build up that much charge, you build up a Coulomb, and lightning isn't the right word for what you'd see. Actually, it is. Okay, so there's your node F. And again, we can write any one of these in terms of the other two. So we're only going to have 2 currents. So all we need is 2 equations once we've done that. Now, actually, we've got 3 equations. This equation, and this equation. We reduce it to 2 equations by letting I1 equal I2 plus I3 But the notation is going to be a little simpler, so I'm actually going to say we're going to let I2 equal I1 minus I3. And now we can write out these equations. So we're going to have how can we go here? Okay. Well, I'm going to start over here. L I1 dt plus R1 I1 plus R2 I2, but we're letting I2 equal I1 minus I3. Equals 0. Then using the derivative down here, we're going to have R2 the I3 dt. I'm going to reorder these, put them in a prettier. Just line things up a little bit, but we're going to just write it down. R3 I2 prime is di2 dt equals 0. So well, let's do this in decreasing order of the derivatives. And I'm going to write the second equation first now. We have R2 the I3 dt minus R3 di2 dt plus I3 over C equals 0. And then we have L the I1 dt and negative R3 the I2 dt, and something's wrong there. And what's wrong is I started out looking at this equation. And then I started looking at the second equation. And that's not right. Okay. Looking at things carefully, here gives us this. And then I have an R1 I2 R1 I2 and R2 I1 and an R3 I3 from the distributive law and so forth. And that's my first equation. Now, what I probably should have done is ordered things with I1 first, I2 second, I3 third. What I have is a system of non-homogeneous equations. I could write my derivatives here. And then on the other side, I can have my I3 over C, and actually Actually, I'm not going to go into how we solve these things. We write them out as a matrix equation. The matrix equation could be written as I shouldn't have an I3. Because I don't want a system with 3 equations. The reason I did this is get a system with 2 equations. So I pretended to make that mistake. Now I'll fix it. Okay. So we have I've got a di2 dt here that I didn't deal with. When I looked at this, I thought I was taking care of everything. I wouldn't have to do that. But this is actually going to become d I1 minus I3 dt. So we're going to have a di1 dt and a di3 dt here with the R3 in front of them. I'm not going to go through the rest of that simplification. I'm just going to say now that our equation is going to be in terms of I1 and I3. And I'm telling you more than the book is going to ask you, but I want you to see kind of where this is going. Okay, we have I1, I3 prime. Yeah, I can't write that either. Okay, I'm not going to write this. Yeah. I'll go ahead and write out these equations. We have R2 plus R3 times di3 dt, and it should be clear where that comes from. Lowercase I. Okay. Now often we'll multiply through by the C here because denominators are a pain. So I'm going to do that. So that's what we get if we simplify this equation the way we ultimately really want to write it. Then we're going to have L di1 dt plus okay, I wrote out I1, I2, and I3 here. I want to use I2 equals I1 minus I3. See if I can make that fairly clean. A little bunched up. But I replaced I2 with I1 minus I3, should have done that in the first place. And now we see that we have for I1, we have an R1 plus R2. And then we have a R1 plus R2 I3 equals 0. And now everything is in terms of I1, I2, I've got the wrong subscript on here. I have R1 plus R3 times I3, not I2. Okay, now everything is in terms of I1 and I3. Every I is an I1 or an I3. So now we have two variables. So now we can say that C times R2 plus R3 I3 prime for this one we have this. Okay, so this derivative and this derivative can be written like so. And then we have Li1 prime is equal to negative I3 is equal to this. So we have a derivative of a vector involving I1 and I3 equal to this sort of non-homogeneous case. And this is not exactly how we want to rearrange it, but this is the most obvious rearrangement. And again, we're not going to go too deeply into this. I do kind of want to go to one more step. So we have then factoring these constants out. This matrix times this derivative of the I3, I1 vector represents this. And this matrix equation represents this. And now we have the vector equation in terms of I3, I1, derivative of I3, I1 vector, and the I3, I1 vector, and I wrote those backwards. And to solve this equation, we're going to do some eigenvalues to solve the homogeneous equation. This is 0, and they get a particular solution for this equation. So you can kind of store that away. This is what we do with this equation. Now, we're not going to go into these details. I hope maybe we can look at those details later in the course, although systems equations inexplicably it is not covered in this course. Well, there's an explanation. It's been decided that we want to do more with the Laplace transforms. There's only so much we can do in the course. Okay, well, it's a little clumsy with all that, but it all holds together. And it comes down to, again, where in the world is it? Okay, yeah. Okay, comes down to, again, the ability to write a system in terms of just currents and their derivatives, giving us a first order system, rather than charges, rates of change of charge, and rates of change of current, which is a second derivative of the charge with respect to time, which would give us a second order system. So we'd have second derivatives, and then those matrices would be bigger and require a little more technique that we don't want to get into. Okay, well, this is important stuff depending on the engineering that you tend to pursue. From what I hear from your colleagues in the physics class, one of them is doing computer and electrical engineering. Another has gone mechanical. In mechanical engineering, as you might well understand, all this has analogs in mechanical systems where you have harmonic oscillators and so forth. And they're direct analogs. Okay, you have second derivatives of position and first derivatives and all that stuff. And you can have systems of mechanical devices that are totally analogous to everything that you see here. And we're going to touch on that a little bit in the next chapter. Spring mass dashpot systems, where you have forces that give you second derivatives of position, like in a spring. Forces, in other words, forces that are proportional to acceleration. You have drag forces that are proportional to velocity. And then you have just plain old forces. So you have forces that are derivatives and they're second derivatives. And I didn't say that quite right, but we'll draw out those analogies later. Some reason my brain isn't working particularly well this morning. Okay, well, we'll draw the analogies later. Its equations end up looking very much the same. Okay, I'm going to pause the recording and see what else we want to look at. Okay, so now, let's take an equation like now we have second derivative here. Everything we've done before is confined to first derivatives and the function itself. Okay, but turns out this is very easy to handle. Okay, so assume y equals e to the RT, or a multiple of e to the RT. Let's go ahead and do a multiple. A e to the RT, where implicitly a and r are constants. And it's very quick. If you take a derivative of this, chain rule gives you an r out in front. So y prime is r a e to the RT. And if you take a derivative of that, well, r and a are constants, so they don't do anything, but chain rule gives us another factor of r, and you get an r squared a e to the RT. So what we get is r squared a e to the RT plus 3r a e to the RT minus 4a e to the RT equals 0. Now there's there's a motivation for using this exponential, because go back to just first order equations. You solve y prime plus little p of ty equals 0 by you essentially assume that you have a solution of form ae to the RT, and you find that r has to be an integral p and all that stuff. Now, and yeah, just go back to one of the first things we saw. How do we deal with first order linear equations, first order linear homogeneous equations? Okay, non-homogeneous equations, there's some complications. I'm not going to talk about those right now, but yeah, we'll get to them. Okay, so there's some motivation for this, and I don't want to go any deeper into that idea. Just by analogy, maybe with what we did with first order equations, we can make this assumption, and it turns out it works out. Okay, for any system, for any second order equation with constant coefficients, this is going to work. Now, if your coefficients aren't constant, well, then you get reduction of order and stuff, and you're going to see about that. Okay, we have this. If we look at this, we've got an AE to the RT, an AE to the RT, and an AE to the RT. So we have this simple quadratic equation. Now, if this is a third order equation with a y triple prime and a y double prime and stuff, we'd have a third degree polynomial. Okay, and we have to solve this polynomial. Okay, well, there are various ways of solving it, and we learn those in pre-calculus, and maybe deal with them a little bit in calculus, and a little bit more here. Okay, so r equals what? Well, this factors into r plus 4 times r minus 1 equals 0, meaning that r would either be negative 4 so our solutions are okay, well, I'm going to write this as C1 e to the negative 4t. Now, the constant here was a, but a could be anything, so we're just going to let a be this constant. So we're going to call that solution y1, and a solution y2, which is C2 e I'll just say e to the t, because r equals 1, so e to the rt is just e to the t. Okay, so that's going to be C2, make it look a little less like an E. So we get these two solutions. Now that's very simple. Okay, once you've done it once, you pretty much have it as long as you remember to use the substitution, and that's the key in solving these equations if you have constant coefficients. So as long as you can solve the equation here, which is called the characteristic equation, you can write down your solutions. Okay, well, that's what we have. Now, just like with first order equations, we could do a geometric argument. I'm not going to take the time right now, just trying to give you a quick overview. You have an arbitrary constant with a first order equation. Well, with a second order equation, you have two arbitrary constants. So I have a C1 and a C2 here. So general solution okay. With a first order equation, through any point, remember, you get a solution with an arbitrary constant. Okay. That arbitrary constant would correspond to an initial condition, which tells you what y would be when t equals or x equals 4, whatever. Okay. With a second order equation, you have two things going on. Okay. The first order equation just gives you the slope at a point. So if you got the point, you can always calculate the slope and then recalculate the slope and so forth as in Euler's method and get at least an approximate curve. And if you shrink the interval of approximation down to 0, you get the solution curve, with one parameter being the value of the function at a given value of x or t. And second order, it's a little more complicated. If you know the y at a given t, that's great. But then you also got to kind of know y prime at a given t, so you can predict y double prime and see how to build the curve. Whether you understand that or not, that's kind of the geometric connection. And we'll talk more about that when we have time. Okay, well, here's your general solution. And you have two parameters. Okay. And in light of what I said, given, let's say, let's just say y of 0 and y prime of 0 now, or any combination of values and derivatives at 2 points. Okay, a value or a derivative at one point, a value or a derivative at another point, which would be like y of a and y of b. It doesn't have to be y of 0 and y prime of 0. A and b don't have to be the same values. Although if they are, it's a whole lot easier to solve the equations. And they're not hard to solve anyway. Or at 2 different points, the value of y at one and value of y prime at the other. Of course, it could be y prime of a and y of b, or the derivatives at 2 different points. You plug those into this equation, and you get 2 simultaneous equations for C1 and C2. And that's what your homework is going to be looking at. What you do if you have this general solution and then have some initial conditions. Now let me just look back and make sure that I'm telling you the truth. Yeah. We still got 10, 15 minutes. I'm tempted to do an example of this, but I also need to talk about the Wronskian. If y of 0 is 3, y prime of 0 is -2, then remember that y is this. If we plug in t equals 0, well, y prime is this, just take the derivative. So y of 0 equals 3, well, the t equals 0, and y is going to equal 3. So 3 equals C1 e to the -4 times 0 plus C2 e to the 0. Or C1 plus C2 equals 3. Got that 4 in my head because it's the first thing I'm going to have to do over here. That's from this equation. From the other equation, we have y prime of 0 equals, what was it? -2. So from this equation, we get -2 equals -4 C1 plus C2, that is -4 C1 plus C2 equals -4. Well, that's two very simple simultaneous equations you can solve for C1 and C2, and you get the specific solution, okay, to the equation. Okay, well, that's pretty simple. Okay. What we want to say now is that for this example, and I rebuilt my frame back here and just getting used to the way it goes uphill. I've got to do something about that. Maybe get my camera a little different. Maybe the camera's a little off center. Maybe that's less to do with the frame than my setup. Okay, anyhow, for this example, your general solution y equals C1 e to the negative 4t plus C2 e to the t. It's an arbitrary, and one R in there, arbitrary linear combination of the set e to the negative 4t e to the t. And I can say in terms of linear algebra, and you want to be sure you kind of maintain this terminology. Set of solutions of our equation is the span of this set. Now you want to have that terminology, especially if at some point you get into systems of equations. And, you know, I know that, well, Dimitri is doing the computer engineering stuff and Elam is doing mechanical, okay? I don't have any good feedback on them recently, but where Dimitri is, I know he's into systems of differential equations because they're doing circuits. And I assume Elam is into systems of equations because he's doing mechanical systems, okay? Now I know a little bit more about how utterly important circuits are in electrical engineering than I do about exactly what goes on in a mechanical engineering curriculum at the junior level. It might even be a senior. So I don't know. Anyhow, you're likely to run into systems of differential equations. So this language and this terminology is something you want to kind of keep a hold of, and also kind of motivates, or we might want to do at least a little bit with systems of equations. There's a whole lot that I always do, but we've reduced the course down to 3 credits, and we can't do it all. We didn't do it, the system did it. Okay. Okay, now, our solution set is linearly independent because the Wronskian, which I'll define in a second, of the set e to the negative 4t e to the t equals the determinant of the matrix that consists of first row being the 2 solutions, second row being the derivatives, first derivatives of the solution. If you get higher order, you would need, if you had a 3rd degree equation with y triple primes as well as the others, you'd have to have 3 solutions and you'd have 3 rows, first the solutions, their first derivatives, their second derivatives, okay? Now, what's important about the Wronskian? Well, the Wronskian of this, you're going to get at e to the negative 3t here. And here you're going to get a 4e to the negative 3t. And you can verify that that Wronskian is 5e to the negative 3t which ain't zero ever. Okay, it's never zero. That's your test for linear independence. Okay. You can see how we're typically, at least for equations with constant coefficients, where we're typically going to get exponential solutions. And unless these functions and their derivatives line up in a rare, unusual way, you're not going to get zero. The only way they're going to line up is if these are the same as these. Okay. And if you got different numbers in front of t, it's not going to happen. Okay. Well, that's the idea of the Wronskian. That's how the Wronskian guarantees linear independence. You're going to be asked to evaluate some Wronskians. And you get some pretty weird stuff. You get equations that don't have constant coefficients, but you're not asked to solve them. So in the first section of chapter 4, you're just going to be given solutions. Now, I wanted to show you where solutions can come from. There's a whole lot more we can do with reduction of order and non-constant coefficients and so forth. But if you have constant coefficients, it's always like this. One more thing, terminology. For this one, for this equation, this is a general solution. That's what we mean by general solution, a solution that has the appropriate number of arbitrary constants, that number being equal to the degree of the highest derivative in your original equation, which would be 2 here. So you got 2 constants. Your particular solution, and I can solve this for this equation. We just subtract the second equation from the first. We get 5 here and 5 here. So C1 equals 1, and then C2 is going to equal 2, I think. So if I take this solution, this system of equations, I think C1 equals 1, C2 equals 2. I did it in my head. My head's pretty unreliable this morning, which is too often the case. But if that's true, so here's our general solution. Plug in C1 and C2. We're going to get e to the negative 4t plus 2e to the t. Again, we can test that and see if I got the right solution. That my point here is that this is a particular solution. Now that's terminology you've seen, but we want to make sure we see how it applies if you have a higher order equation. Just another comment, and we're probably not going to do it since we're not officially doing systems. If you have this higher order equation, it can be reduced to a system of 2 first order equations and solved in a way that's totally compatible with what we get here. Okay, well, that's the terminology. Those are the ideas you're going to need in the first section. And I think you'll have no trouble with it. So good luck. Have a good weekend. Any questions or comments?
I think I'm good. Thank you.
I think you're good. So